a lot easier to do the hand raise when you're in class if you want.
Did you try to do it when we were like talking over the Skype call?
There we go. Even if Taylor's back's to me, she'll be able to hear the hand raise. I apologize for the distance stuff, as I try to accommodate you guys when you have things that happen in your lives. I hope that you respect me and give me some of that as well, so I appreciate the patience. With that said, do keep in mind, if stuff does happen in your lives, like it always does, and it keeps you from being able to do your best here in class, don't hesitate to reach out to me. I know that you guys, that we all have lives, that stuff doesn't always go as you want, so just send me a note. It's much easier to help work with you if it's before things actually happen, like before you miss a class or miss an exam or a homework. I can work with you. It would have to be the kind of thing that I could tell another student in class, hey, they say, why did you get an extension? I say, this is a reasonable thing. So it's not like absolutely anything, but if it's a reasonable support that you need, I'm happy to provide it. So today's class, we're going to build off of the kinetics we've been working on recently. So here's our first question. Go ahead and take a minute. If you have not already, please make sure everyone at the table knows each other's names. If you have your table name cards, that would be even better to put those out. Introduce yourselves to each other really briefly, and then try to figure out how to answer this question, please.
Email earlier and now it just completely kicked me out.
No, you're not creating an account though.
I know, but it won't let me. It says it's not found anymore.
Use your old email?
Yeah, because I changed it. I changed it on my school email after you emailed me, but I don't know what happened. So now it's apparently not found anymore. Keep typing it in.
So you forgot password, and then put in your UALR email. That way you'll choose it. How are we doing this problem? Any idea where to start? No idea where to start? Let me hear from Nick first. That's all right.
So I just beat because of the
Double the, careful, say rate. We're talking about rate, the speed.
correct. So just as opposed to the 1 and 2.
Okay, so think about a better description of that. Your logic start is great. Think about how to make that like a full sentence, describing that, and you guys help, all right? What are we thinking?
I'm trying to figure out which equation to use.
No equation.
Nope.
Get rid of equations. Stop thinking in equations.
So is it just a lucky guess?
Why?
Because it's 2 NL versus 1 L2.
Okay, so think about it in a more logical argument kind of statement. So we're talking about the rate of consumption of this. So how is this going to compare to this? And think about how what you just said kind of can be a bigger argument, right? Why is it 3.6? Because this is based off the data you guys had under your last worksheet.
Instead of negative 1.5.
Or 7.6, around there. So I try to streamline it for today because we kind of need to do it today. Alright, a couple more seconds, clicking what your group has decided, or if you disagree with them.
So what do you got then?
So would that work?
It's not balanced.
It is a mistake. What should be different?
It's supposed to be 2 NO.
It should be nitrogen dioxide.
Mm-hmm.
Just write it out.
So someone pointed out a typo. Sorry about the typo. We're not doing magic disappearance of O2. Not what's happening. Okay. So everyone submit a result. Make sure you add that 2 on the products, so it's nitrogen dioxide as the product, not nitrogen monoxide. Alright, should we take a look at the results? Do you think that the class was in agreement? Well, there's a majority answer. So can I get this group here at the front, table number 4, to share your logic of your answer and what you chose and why? Maybe Nick, do you mind discussing what you talked about with the group?
So we just figured because there's one coefficient from O2 as opposed to 2 from NO, we figured we'll just double the rate.
Okay. Does anyone want to add to that? I think that's a really good starting point. I think there's more to it that we can think about as far as like how that logic plays out instead of, in addition to looking at just the stoichiometric coefficients. What do the stoichiometric coefficients mean, and how do we use that to strengthen that case? Anyone in the class can volunteer. Okay.
I'll tell you what the stoichiometric coefficient is basically the coefficient from the elements that you use to balance out the equation. And you'll use that because per the amount of moles it takes, like for this one in particular, I believe if there's a 2-to-1 ratio, then the one with the 2 is going to burn up twice as fast as the one with the
You guys follow what Kat's saying? So basically what Kat's saying is that in order for that reaction to happen once, you have to consume 2 NOs for every 1 O2. That means it's being consumed twice as fast because there's a stoichiometric coefficient of 2. So if this wasn't a balanced equation, you would have to balance it because, like the mistake I made, right? You don't create or destroy matter. It has to exist before and after the reaction. The only time when that kind of gets a bit wonky is nuclear reactions. But then you technically conserve mass, but that's the only time you actually change the number of elements. So for a reaction like this, it's not a nuclear reaction, it's a chemical reaction. We have to use twice as much NO in the same amount of time as we're using oxygen in order to create these products. So that means the rate has to be twice as much. So I concur with the majority of the class that we can look at these and say that the relative rate of consumption is going to be based off the stoichiometric coefficients. So let's then, see I had it right on the next page, somehow I just lost the 2 and I copy pasted I think. So go ahead with your group then and discuss what the rate of production of nitrogen dioxide would be. I'll give you about 45 seconds for this one. And I want you to work in groups to put together the sentence that describes why you chose the answer you did. Did my question make any sense when I came over here and you said it's 2 because the stoichiometric coefficient is 2? Do you understand how it's like? Why? Yeah. So by making a sentence out of it, it's not going to put some context. So can you guys do that for this one as well?
Twice the amount, then you would have to multiply the 1.8 by 2. But since it's being created for production instead of consumption, it would be positive.
Okay. And so not because we need, but because we make. I would use that term because it's on the right side of the equation. Kind of what you're getting at with the positive negative. But you said it would need double the amount of NO2. we don't need it, we're making double the amount of NO2 compared to the amount of O2 we're using. Does that make sense?
It seems like we need to, like, to do it, but we need to do it.
All right, a couple more seconds. Closing out. How confident do we feel on this? 19. There we go. All right. So we have a mix. We have both B and D. So it seems like maybe one table went for B, and the rest of the tables went for D. So can I have someone explain your group's logic, which answer you chose, and why, and try to use some of the terminology that I used towards the end that Kat kind of alluded to with the stoichiometric coefficients. Volunteers.
We picked D because it was production of NO2. That's impossible.
Okay, so there's a couple things we're talking about. So one is the numeric value, and two is the sign. So you said you picked the positive one because it is a production as opposed to a consumption. So that's just positive versus negative. Okay, everyone follow that? Seems like no one picked a negative sign, so that's good. But then how do we choose between B and D? How do we choose between those two? Go ahead and make a sentence out of it, if you will.
So on the consumption side, it's the same coefficient as a production for NO. So that's why we put.
Okay, great. So the coefficients are the same for NO consumption and NO2 production. So can I have someone put that in a sentence for what that means about the rate of consumption versus production?
It's the same.
Sentence?
The rate of consumption is the same as the rate of production.
So almost there. Fill out the rate of consumption of and the rate of production of.
Of the reactants.
Not both. Amber, you want to help fill out that sentence?
The rate of consumption of nitrogen oxide would be the same as the production of nitrogen dioxide.
Because they have the same stoichiometric coefficient. So a stoichiometric coefficient in an equation tells us how many of each thing has to be consumed for the reaction to proceed one time. And if it proceeds 10 times in a second, or 1,000 times in a second, or this many moles per second, so remember we said that nitrogen monoxide consumes 3.5 times 10 to the negative 6 molarity of it is going away per second. That's a lot of molecules that are going away. So if that's the case, then at the same exact time, that exact many molecules or moles of NO2 are being formed per second at that exact time. And think about it this way. We're saying we're starting a reaction. This is the initial rate of reaction. We have a reaction vessel set up. We add everything, and we start clocking it right away, and we say how much reactant is being used up. And we only measured one of them. Jesse had a good question. He said, what the heck? Why is 1.8 times 2 3.5? The reason is because I modified some slides that were at the end of your worksheet last time. So if you look at the actual initial rate, it was actually 1.76 times 10 to the negative 6 molar per second. So that's why I rounded to 1.8, and then double that was 3.5. So sorry, there's a little bit confusing there. These numbers should be double or half because we're talking about 2 to 1 stoichiometric coefficient. I hope that's not too confusing. Okay, let's do, we already talked about the initial rate. The last thing I want you to do is go ahead and click in the rate of reaction. And we're just going to do this numeric. What is the rate of reaction? Just put in the number. We're going to assume the units are the same, molarity per second. So it's the question that's in the box. I got your you don't mind making a pile of index cards in the middle of the table, the ones that I gave out for table cards, pick those up. We have 12 responses. The rate of reaction. Sometimes. All right, I'm going to do another 15 seconds. Go ahead and put in an answer, see what you think. Closing out. Okay. Can I have a volunteer from the back table? Sam? Danielle? What is the rate of reaction? How do we think about that? Okay. Toss the potato over here. Rate of reaction. What is that? How do we figure it out? Patrick?
Is it what we started with?
Why?
Because it's what we started with.
Okay, so that's one idea. Is it what we start with? I also heard it's the lowest rate of any of the reactants being consumed. That it's actually, neither of those logic are the reason why, but answer B is would be the rate of the reaction. Why? Why is 1.8 times 10 to the negative 6 molar per second the rate of reaction? By the way, that is very, very different from that. Right, 1.8 is not 1.8 times 10 to the negative 6. That is a much smaller number. I said no units. That doesn't mean you can make it 10,000 times bigger. Right? That's a very, very different consumption rate. So why is this the rate of reaction? No one's super comfortable with it? It is the easiest possible easiest possible rate to come up with, because it is whatever the rate would be for something with a coefficient of 1. So you might have something with a coefficient of 1. We did in this, right? O2 had a coefficient of 1. So whatever the rate of consumption of that is the rate of reaction. And it is a positive number, always. What if you don't have a coefficient of 1? Divide it by the
number of coefficients.
Whatever the coefficient is. So if we only knew the rate of consumption of NO, how much would we divide the rate of consumption of NO by to find the rate of reaction? Divided by 2. Because then we would have found the reactant that has a coefficient of 1. The reason why it's so nice and useful is because if we have a reaction and we only have the rate of reaction, we can then multiply it by a stoichiometric coefficient to find the rate of consumption or production of any of the reactants or products. It's just a simple multiplication by the stoichiometric coefficient. So we're going to do a problem like that in a second. You'll probably see it's the next problem coming up there. But before I get to that, let's talk about the exam and then what I want you to be able to do by the end of the day today. Any questions? Well, we'll do questions on rate of reaction as we get more forward. So I got back on campus today, and me and Humindra spent most of the day today grading the exams. I realized that there was a question that didn't have an answer. because if you found the Van Hoff factor, it was like 23, and it was supposed to be 2.3. So I removed that question because it was a crap question. So I apologize for that. Every once in a while I make a mistake. And if you are taking one of my exams or any professor's exams and you find what you think might be a mistake, do not hesitate to flag down myself. I'll usually be here, or whoever's proctoring the exam. They had my phone number. They could have called me and been like, hey, a couple people are saying that they can't find a number that makes any sense here. So follow up with that, okay? I make mistakes. I write all exams from scratch. That's why I post all my old exams online, so you have study material and you know what to look for. But that means that I might make a mistake when I'm making exams. So I removed that question, so there's 19 multiple choice questions. Short answer, I did have to shuffle the points around because when I was making this, I was not the clearest of head, and so my math skills were not great. So you'll see the answer key in the exam is now posted to Blackboard. You can go look at that. You can pull it down, and you can see how the points are distributed slightly differently in the short answer. And then based off of that, we've posted the grades. The average on this exam was 71.8%. If you did not do, which is actually pretty high for Gen Chem 2 first exam. Averages are usually in the mid to upper 60s. So I think overall this class did fairly well. So I'm proud of you guys. If you didn't do as well as you wanted on this exam, does that mean you're done, you should quit? So this is the first exam out of 4. The final exam, if you do better than another exam this semester, the final exam score replaces your lowest exam score if it's higher than that lowest exam score. If you do worse in the final exam, it doesn't replace anything, it doesn't double count, it's fine. But that means that you have a chance to learn the material that you missed on this past exam, and then show in the final exam that you know how to do the material, and then you'll be able to make up for that. I have office hours 1 time scheduled per week, Mondays now, 3 to 5. That is a really good time to come and work through these things. That is chosen based off the availability of the people who answer the poll. Please come see me. If you can't come at that time, send me a notice. Say, hey, I'd really like to meet Thursday, here's my availability. I'll make it work. So if you feel like you're not making progress, I'm a resource for you. Even in the next week, I'm going to be out of town again next week for a bit. Send me a notice, and I'll figure out a time. I'll do a Zoom chat, and it works almost as well as being in person. I can write on the screen. You can show me pictures. It actually works really well. So keep that in mind. I'm your biggest advocate, but I can't help you if you don't come chat with me or come meet with me. You also have the tutoring center. You have the math assistance center, because we're going to be doing logarithms coming up soon. Logarithms are not easy, especially if you are rusty on them, so make sure that you get caught up on that. So use your resources. If you aren't where you want to be right now, it does not mean by any chance that you're not going to do all the rest of the semester. All right. By the end of today's class, I want you to be able to predict how the rate of reaction depends on the starting concentration of different reactants. So that's our rate order that you guys have already started with. We're going to use more experimental data, see if you feel comfortable with the stuff that you worked on in class on Monday. And so then we're talking about all of this kind of adds up to describing how a reaction proceeds with the speed of consumption of the reactants and production of products. So that's called the rate law. Then we're going to take a look at the next step, which is what your primer was on. And then looking at some more complicated sets of data, if we look at the concentration of one reactant over time, not just the initial rate of reaction, but if we look at how much is consumed over time, can we tell from that instead what the rate order is? And so we're going to have 3 different plots that we're going to use. We're going to take the same data, look at the concentration over time, and then we're going to say, well, what if we looked at the natural log of that concentration instead, or the inverse of that concentration went over that? And from that information, we'll be able to glean the same type of information that you can calculate from having multiple reactions to look at multiple experiments. Hopefully by the end of today's class, you'll feel pretty confident in that. But that means we have to move pretty quickly. So I'm going to try to keep up a decent pace. And I hope that you flag me down if you need assistance, or you can stay after class a few minutes and chat about some of those things if you're not. So let's figure out how to answer this question, which is question number 2. Is that right? Sorry, question number 4, and answered question number 5. As soon as you answered question 4, please answer question 5. The clicker is just question 4. just clicking in the answer right now, and then we'll figure out the second question here in a second. All right, I'm going to go ahead and close out. Were we mixed on this? Feel confident on this? Thumbs up. Confident. Not confident. Down. So we have a majority of the class answering that the production of E is going to be faster than the consumption of A. Sarah Ray, do you mind sharing why?
So the consumption of, three A's is slower than the production of 5 B's.
Yeah, and I can maybe even tweak that a little bit and saying in the time that we consume 3 A's, we produce 5 E's. So that stoichiometric coefficient is the only thing that matters. That doesn't tell us what the rate constant is for A and B. The rate constant says if we double the concentration of A, does that rate of reaction change or not? The rate of reaction is going to be determined by the concentrations of them, but whatever the rate of the reaction is, we can't consume 3A unless we consume 2B. So that means at whatever time frame we consume 3A's and 2B's, we make 4 D's and 5 E's. So how would we actually calculate the rate of production of E? Samantha?
Have 2B is the lowest coefficient, so you have to divide everything by 2 so that you can get a coefficient of 1. And then
Pause. Does everyone agree? Stacy?
I disagree,
Why?
because it's giving you the rate for A, so you have to divide it by 3 and multiply it by 4.
Why would we divide it by 3? Why would we divide the rate of consumption of A by 3? It's not called the initial rate. Well, all this is initial rate. All is at the beginning of the reaction. What's that rate that we're trying to find called? The rate of reaction is independent of any reactant or product. The rate of reaction is whatever the baseline is, and it's not necessarily the smallest coefficient, so careful. The last one happened to be 1.
it doesn't matter what happened to the initial rate. That does not.
So all of these are the initial rate. If you look later on in time, the rate's probably going to be lower because most reactions, the rate depends on the concentration. As you're using stuff up, there's less of it there. So the rate's going to be slower. That is not the case for zero-order reactants, and hopefully in class we'll get to that today. But for most reactions, the lower the concentration is, the less you have. So that's why we always talk about the initial rate. So at the exact snapshot, we're looking at the consumption of A. We know that the rate of reaction is going to be 1/3 of that. So what is the rate of reaction? Can anyone tell me what they calculated? Stacey?
I got 9.5 times 10 to the negative 4th in S.
Molar consumption per second. That is our rate of reaction. I like that you didn't put a sign on it. Because if we're saying the rate of reaction, it never has a sign. Because then what we can do is we can say, okay, we know that the rate of consumption of A is 3 times that. And it's the rate of that reaction that's a negative sign because it's going down in concentration. What about the rate of consumption of B? How would we find that? Multiply what by 2? Great. We multiply the rate of reaction by 2 to find the rate of consumption of B.
We were thinking that was.
Be the rate of production, not the rate of reaction?
Yeah.
Say again?
Like, because you divide, like,
Oh, so the number you gave me was actually the rate of production of E.
Yeah,
Sorry.
I'm
I wasn't even doing that.
I wasn't-
What is just the rate of reaction? Sorry.
So you just divide it by 3.
Yes.
1.9 times 10 to the negative 4 in per
Times 10 to the negative 4. That sounds better. I wasn't even thinking about the logic of why. So Stacy was jumping one step ahead, and she was doing the next step as well. So that's exactly what we need to do, but I want us to focus on the rate of reaction first. So the rate of reaction is something now we can multiply out, and so I think Stacy multiplied that by 5, is that right? To find the rate of production of E, because it's 5 times that amount. Thank you for catching that. Okay? So here's how I want you to work these problems. Anytime you have the rate of consumption or production of any of your reactants or products, first step, if you're trying to find the rate of one of the others, is find the rate of reaction before you do any other calculations. Because what your book tells you and a whole bunch of other places tell you is you do this thing where you would divide by 3, multiply by 5, all in one step. I think it's so confusing because then you're like, wait, is it the reciprocal or which one do I multiply and divide by? Just find the rate of reaction. Once you have that, you can just multiply by any stoichiometric coefficient and you can find the rate of consumption or production of anything. So the rate of production, so we would do 5 times 1.9 times 10 to the negative 4th molar per second is the rate of production of E. Tina?
Sorry, why did you pick 3 for the first one?
Can someone help out? Why did I pick to divide? You were saying, why did we divide 5.7 by 3? Okay.
Because the stoichiometric coefficient of A is 3, so that means it's 3 times the rate of reaction.
So, Tina, just to be clear, we're on the same page? That rate of consumption was for A, and so A is 3 times the rate of reaction. Does that work? By the way, a very important point I should bring up after grading your exams. You all like to round, like a lot. Don't round at all. If you're using calculators that have the ability to store a number, which these ones do, you can store, I think, 3 or 4 different numbers in them. If you're not sure how to do that, come talk to me, I'll show you how to do it. Store the number, that keeps the number in its entirety, and you don't have to round. So a number of you ended up getting answers that were incorrect and you lost credit because they were off, because you rounded multiple times throughout your problem. Only round at the very end. If you're giving an answer, that final answer is when you decide how many sig figs and round. Nothing else should be rounded all the way down. And if you don't know how to store, that means you're going to be writing a lot of digits on your paper, and it's a pain. So figure out how to use your calculator to store. Either just Google a YouTube video, how to use store function. On the TI-80s, it's a lot easier. And you can store them on the calculators you borrow from us as well. The only exam you can't do that on is the final exam. You can't have a graphing calculator for the American Chemical Society final exam. So keep that in mind. All right. Could you do this on your own then? If I gave you a really complicated equation and I gave you one of the rate of consumption or production, could you find the rate of reaction and the rate of production or consumption of anything else? If you can't do that, then that's something you want to work on. This process is what I need you to be able to do. So I think that's one of our learning objectives today. Second thing that we did on Monday was we said, okay, we know that we can compare how fast things are consumed to each other through the stoichiometric coefficient. But let's think about if we want to say, well, what if we increase the concentration of one thing or another, then how fast does the reaction go? So here is a much more complicated reaction than you had in class last time. It's called the iodine clock reaction. In the top right corner here, you can actually see this reaction. It's super cool. It's a clock because it actually goes back and forth. It goes black and then clear, and then black and then clear, and then black and clear. And it's instantaneous like that. It's a really, really bizarre reaction. It's all about this weird equilibrium that's going on. So you have all of the information here. I want you to take about 1.5 minutes, look at all of the data here, and try to figure out how we're going to determine what the rate law is for this reaction. And before you dig into it, I know that Ms. Katoon worked with you on this, but I want to just kind of set the stage for the way I think about this, and hopefully it helps. So ignore the numbers for a minute, if I can get everyone's attention. This reaction exists. It happens. These things combine and they make the products. So what we're going to do is we're going to take 4 separate beakers. We're going to have experiment 1, and a separate beaker, experiment 2, a separate beaker, experiment 3, and a separate one, experiment 4. And those 4 beakers are all going to have different starting concentrations of each of the reactants. And somehow, which we'll talk about a little bit later in class, we're able to measure how fast that initial consumption of reactions is, or the initial rate of reaction. So this is not rate of one or the other, this is the rate of reaction that we just talked about. Okay? So we're able to measure that, and we do that for each of the 4 reactions. This is the initial rate, this is the initial rate of reactions. So I want you to spend a minute and a half to look through all of these values on this table and see, we did the experiment and these are the conditions and this is how fast it was. These are the conditions, this is how fast. These are how fast, this is how fast. Figure out, what does that tell us about each one of the reactants and how it influences that initial rate of reaction? Okay, so go ahead and take a minute and a half. You can talk to people at your table if you want. I want you to just try to set the framework. You don't have to start calculations yet. Think about what the information there tells you. By the way, I'm not sure if everyone knows, there is a restroom behind that barn door if you ever need to use it. It's kind of awesome. We have a private bathroom. If you need privacy, you can go out.
But what does this mean?
True. So what does that mean? What are they used for?
H2O2,
Yeah,
which
that's
is
what they're called.
hydrogen peroxide and iodine.
And so it would be, now we have three different ones, right? Before it's M and N, because there's two
The
reactions.
initial rate.
Now we have three reactions.
You get to discover what.
So what is the rate? What does it tell us? So the rate order tells us, go ahead.
It tells us how the overall rate responds to how its individual rates. So if the H2O2 doubles, the initial rate also doubles.
So the concentration relates to the rate. Follow what I'm saying? So if the concentration of H2O2 has an impact on the rate of reaction, you change the concentration of H2O2, everything else is the same. You're going to see a big change in the rate of reaction compared to the concentration, like relative to the change in concentration or something like that. If it doesn't influence the rate of reaction, then you can change the concentration of it, nothing.
Or try one.
So go ahead and see how you can look at these and see if you can get what my friend suggested.
But when you're
So you're going to have to compare multiple experiments to see. You can.
But when this doubles, right here,
That's a question.
so.
Oh, just, it's a bad idea to do exams after.
I don't know, like, the thing, but as far as I can tell for this, see, this is your, but this is your like initial reaction for experiment one with these numbers. And you're messing with these as your independent values.
So like,
Very mathematical
This
description.
doubles, this doubles. And when this doubles, this doubles, but when this doubles, this one stays the same. This means that these are proportional to
Okay,
these two,
so
but
this
it's
is not what
exponential.
you're actually doing. So it's mathematically we can get over this, but
But I don't know, just finding like.
experimental with that, why are we doing that?
Now,
to
even
figure out the order
What does it order mean?
I believe it would be.
Absolutely not.
I'm not sure, but I think you can just like
Isn't it,
tell you more
You guys talk about it. We're gonna. Okay, so can I ask Michael, can I ask you to share your thoughts, and I'm going to frame the question. So, the initial conversations I heard around the room were, oh, this is what we did last class, this is where we find M and N, the rate order. Okay, yes, but why? And so, Michael, can you kind of describe what it is that you talked about with all these different experiments and all the different values? What are we doing this for?
you're finding the order at which the rate changes in response to the concentration change. So if you double the concentration, does the rate stay the same? Does it double? Does it quadruple?
For any one reactant at a time. You get that? That's like super clear. Michael's going to be teaching this class next semester, so I'd sign up with him if you don't like the way I teach. So then if we want to figure out how hydrogen peroxide, H2O2, influences that initial rate of reaction, how are we going to do that? How would I find just the influence of hydrogen peroxide on the rate of reaction?
Only add more.
you find the constant for iodine so that you can find how the rate changes?
So I'm going to combine what you two said, and I'm going to say we're going to do 2 experiments, where the only difference between the 2 experiments is changing or doubling the concentration of the thing that we want to study. So if we want to study hydrogen peroxide, how the concentration influences the rate of reaction, which experiments are we going to look at?
1 and 2.
We look at experiments 1 and 2. The only thing that changes is the concentration of hydrogen peroxide. Experiment 2 is twice as high of a concentration. So then going back to Michael's statement, does that influence the rate of reaction? Yes or no? Yes, it does. What is the rate order for hydrogen peroxide based on just this data right here? 1. Why? Because it's proportional. So remember, our rate law is going to be rate equals the concentration of our reactant, H2O2, raised to some power, times the concentration of I minus, raised to some power, I'm going to call them X now, and raised to the concentration of H plus, raised to the Y power. And the one thing I missed in there is there's a rate constant as well. So what this says is that the rate is proportional to the change in concentration of H2O to the first power. So if we start with a 0.010 for H2O2 and we have a rate, all this other stuff doesn't change when we do the second experiment. So I think that's kind of what Sydney was getting at when I was at her table. She says everything else needs to cancel out. That's one way to think about it. So the only changing function is concentration of hydrogen peroxide. And if we double this, we double the rate of reaction. So we double this to the first power is doubling on the other side. What if that rate order was 2 and we double the concentration of hydrogen peroxide? What would happen to our rate of reaction? It would be 2 times over here squared, so it would be 4 times on the other side. What if it was a rate order of 0? What stays the same? So anything raised to the power of 0 is 1, so it doesn't matter what the concentration is here, the rate is always going to be the same, regardless of the concentration of that one, as long as you have it, right? If you don't have any of that reactant, the reaction doesn't happen and then it goes to 0. So an example of a 0 order reaction is alcohol metabolism. You've probably heard 1 drink per hour. Doesn't matter how much alcohol you have in your system, they say it's 1 drink per hour. Granted, it's not true. That's in like a pretty normal range, from like 1 drinks to 4 drinks, depending on the person. That regardless of how much you have, your liver is still only going to be able to do 1 chemical reaction at a time. And so even if there's a huge line of ethanol molecules waiting, it's still going to go through and do the same rate. So that reaction is only dependent on if there's alcohol present or not the concentration of it. Okay. So we have a rate order of 1 for the first one, and I'm trying to remember, I think I kind of walked through this here. So because the concentration of hydrogen peroxide doubling leads to doubling of the rate of reaction, that means it's first order with respect to hydrogen peroxide. So let's then take a look at the other 2 reactants. So on your own, go ahead and write out that equation. The rate, or that expression, rate equals K times the concentration raised to the rate order. And go through and try to figure out what those other 2 rate orders are. What is it for I minus? What is it for H plus? Use the other experiments in order to figure out what those rate orders are. And flag Diana or I down if you get stuck.
So, I just kind of, when I did these, I just kind of that's kind of like, didn't really look at it first. I guess we had to tell
So you have to pay attention to all of them because you need basically n plus 1 for the number of reactions. Otherwise you can't keep everything the same.
So if there's not a point where this, where this doubles, it changes, that'll change too.
So pick one reactant and then see, once you, so let's do I minus. That's one you want to do. So let's do H plus 1. So let's find.
So would that work though? We could look at that, so I already got it written down, so I looked at this one here, increases.
But Karen, you have two things changing, that's decreasing and that's going up.
Yeah.
So you really want to do one where these two stay the same, and that's the best.
I mean, that's what it changed here.
We're going to experiment one. So let's do experiment one.
I mean, it does count, but I'm saying like,
Define I minus
in
now I
terms
minus.
of increasing the initial.
So if we have this one, experiment one, experiment three, what's that one?
Are you asking about the concentrations or the?
And then.
So the concentration, so these two have to change.
If you leave.
Oh, okay, I see what you're saying, yeah. Oh.
Okay, so.
Yeah, I was, I don't know why I was trying to do like 1 and 2 or 2 and 3 or 3 and 4.
Oh, no, it could be any combination of them that gives you the right answer. Radio six.
Get.
Corrections? So you're actually doing,
So that's gonna be.
yeah, that works as well. So we're able to find each one. Cool. How you guys doing?
So. I think I did it. So that tells me.
So where's your final? Okay. Is that the same as Sam?
I think so.
So what are your rate orders for each of them? And don't forget units once you get there. It looks like you're on the same page for the first one. So we're going to do a numeric answer. Go ahead and click in the 3 rate orders in order. So that's H2O2, I minus, and H plus. Click in the rate orders for those 3. Pronounce your name. I would try to 4. Don't. Yeah, it's bad. It's real bad.
I would offer you a mic and but you didn't remember my name, so.
I don't deserve one. I agree.
For you?
I remember your name. I just don't know how to pronounce it. Did I ask you for your name before I gave you your exam? I feel really bad for others that I do that. I'm not there yet.
Oh.
I got like 1 and 3 for that because it's really hard to read it upside down. I think that's 0.01, and this one's also 0.01, and then you go over here, and it's the same over here, and you can't use this one because you have 0.01, so you can do 5. So then, once you have the one actually.
We have 9 clicks. So go ahead and click in the 3 rate orders, please.
If we're trying to find this one,
What order was it again?
experiment data has to be
Same as this cross here. That.
In a sense.
You were able to get. What's your units? What are your units?
Yeah. Since these two are they're closer to each other. Which two? Ignoring H.
There we got 14 responses. So let's go ahead and talk through the next one. Who? Can I have a new table? Maybe we can call it a back table now. Figure out how you found the rate order for I minus, either Sam or Danielle. Okay, can we get everyone together so we can hear the new group?
When you divide it, it's 2, and then you put up the 2 to the power of what? First order.
So let me go ahead and expand. So I haven't described that way yet, but I think your homework did describe the way you're talking about. So what it says is that you can write out the rate order, and this is going back to, I think Sydney had mentioned it as well. So you can say for experiment 3, we put the rate order for experiment 3 over the rate order for experiment 1. The hardest part is honestly picking which experiments you only change one thing in. So the first one is, I guess, redo. I'm going to erase. So we're actually going to put values in, and we're going to write out the entire rate law for experiment 3 with everything we know over the rate law for experiment 1 with everything we know. So experiment 3 is 2.30 times 10 to the 6, negative 6, molar per second equals a rate constant that we don't know times the concentration of H2O2, 0.10 to the first, because we know that rate order, times the concentration of I minus 0.020 to the x, because we don't know that one, times 0.00050 to the y, because we don't know that one. And we're going to divide that by everything from experiment 1. You guys following where I'm getting these numbers so far? So experiment 1 is 1.15 times 10 to the negative 6 molar per second equals a rate constant that we don't know, 0.010 raised to the first power, 0.010 raised to the power of x, 0.00050 raised to the power of y. Any questions so far on what I've done? So the rate order for experiment 3 divided by the rate order for experiment 1. What cancels out? So our rate constant is the same, unless we change the temperature, which we'll talk about at the end of next week. Something raised to the same number raised to the same power cancels out. Same number raised to an unknown, but same exponent cancels out. So then the only thing we have on the left side is 2 over 1 equals 0.020 raised to the x over 0.010 raised to the x. We can simplify that because of rules of exponents. How do we feel about that? So what power would x need to be in order for 2 to equal 2? So x equals 1. Or you can use logarithms. And you can, if you weren't quite sure and it's not as easy, if those numbers aren't as clean, then you can do log of 2 equals x log of whatever that fraction is on the right side, which would be 2 in this case. Any questions on how we use that approach to find the rate order? Okay? The other way we could have looked at it is we could have said, did anyone do a simpler version of this? What did you do, Sarah? Ray?
I guess if you're looking at like H2O2, you look to see on I and H by itself which ones are constants, and then kind of do what you did, but I don't know.
So I actually don't even do that math version unless I have to. Unless it gets complicated, I don't put something over something. I just look at it and I say, okay, experiments 1 to 3, we were able to hold hydrogen peroxide and H plus ions constant. The only thing we changed was I minus, and we doubled that, and we doubled the initial rate of reaction. Samantha?
On a test, would you want us to put out all of the
No, you would have to justify. So I will say that a few people on this past test, I know this room is not ideal for test taking because you're literally sitting across from someone else, and I'm not saying that people inherently cheat, but if it's a very low barrier and you're stuck, sometimes it's very tempting to just circle an answer because you see that across the table from you and someone had that number. But if there's not justification, I'm not going to give you credit for it. So that's what I did on this current exam, is I'm not saying that people cheated, but I'm saying that if I don't see justification for choosing an answer, especially short answer, on short answer, then I'm not going to be able to give you full credit for just selecting an answer that was a challenging problem. So in this one, if you said, I compared experiments 1 and 3, the only thing changed was the concentration of I minus, it doubled, the rate doubled, first order. Then that's fine. Or you can do the mathematical approach if you want. Either one. I just need to show that I need to infer. A test is supposed to be so I can infer what you're thinking and see if you're understanding the concepts. If I can't do that, I can't give you credit. You didn't earn it. Okay? What about concentration of H+? How do we figure out what rate order that one is? Can I get someone new person from this table? I guess everyone's talked to this table? Tina, you haven't really talked through the problem yet. Go ahead.
He said, sorry, I'm letting it down. So we talked about for the first one and the fourth one, initial rate was the same. So then 2, what power would give us just 1? So we said that one would be 0.
Yeah. So if we compare experiments 1 and 4, the only thing that changes is the concentration of H+ ions. There's no influence on the rate of reaction, and so the rate order for that is 0. I agree. So what's the overall, let's not do this as a clicker, what's the overall reaction order? 2. It's a 1 plus a 1 plus 0. So the overall order of this reaction is 2. And then can we find our rate constant? Can we find, so this is the rate law as of right now. It says that the rate of the reaction depends upon the change of concentration of hydroxide or hydrogen peroxide and the rate of change of concentration, or the change of concentration of I- proportionally to both of those, but then multiplied by some constant, because it's not, if you multiply the concentration of H2O2 and I-, it doesn't give you the initial rate. Right? There's some factor in there that's different. So let's go ahead and calculate K, our rate constant. So let's go ahead and take 1 minute to calculate our rate constant. Pick any single experiment, plug in all the values you have, and the only unknown left should be your rate constant. Think about the units, though. That's the part that most people skip. So what are your units of this? What is it on the bottom?
But I used this, and then the one that you had on the board you did not use.
Because it's to the 0, so it becomes 1 no matter what's inside.
Okay, so then it would just be moles.
Okay.
Right.
You sure? So you have M on the top, you have 2 M's in the bottom. So which one's going to cancel out?
The one on the top.
Better done. How do you say it? How you doing, Kelly?
Basically, just like this right here. Take one experiment. Plug in all the values you have. You don't need this because it doesn't reflect the rate. Plug in the rate. And then just plug in.
That's my proportionality. All right, almost everyone's in. Okay, which experiment did you choose, Gabby, to answer this question? Experiment 1, okay? And you basically just plugged everything into experiment 1? So I think this is all the data from experiment 1. So we know what the rate is, equals the unknown K, rate constant, times concentration of H2O2, molarity, raised to the first power, right, rate order of 1, times the concentration of I-, which is 0.010 molar, raised to the rate order 1. And then we don't even put in H+ ions because they're not in the rate law. And then we solve for our K, paying very close attention to keeping our units. And what we're going to find is that molarity on the top cancels out with 1 on the bottom. And this per second on the top and the molarity on the bottom stay put. Those don't cancel out with anything. So the units are per molar times seconds on the bottom. And so if we know the overall order of a reaction, we can actually decide what the units are. Or if we know what the units are, we can backtrack and say, well, we know the overall order of the reaction. Okay, we have 13 minutes left to do a lot of work. So we're going to shift gears. So just make sure to write out all your units when you're trying to find the rate constant. What we're going to do next is we're going to look at some simplified reactions. Instead of looking at reactions where we have a lot of different reactants in them, we're going to look at reactions with one reactant, and we're going to say, instead of doing multiple trials with different concentrations and looking at the initial rate, we're going to say, let's just look at one reaction. Let's just start it, and let's monitor the concentration over time. And let's see how the concentration changes with time, because it turns out that 0 first and second order reactions also look very different as the concentration changes over time. So the first question I'm going to ask you is going to have us thinking about, just looking at the concentration change over time, what is the rate order of a reaction? So first order, what happens to the concentration over time? How does that change with time? How does the concentration change with time for a first order reaction? Or rather, how does the rate of the reaction change as the concentration goes down? Talk amongst your table for a second. How does the rate of reaction change, the slope of the graph of concentration versus time? How does that change as the reaction proceeds and you have less and less and less of your reactant present? What do you figure this? Okay, so let's do this. Raise your hand if you think that as the concentration of your reactant goes down, so does the rate of reaction. For first order, does the reaction of the rate go down as the concentration goes down? As the reactant gets used up, does the rate of the reaction go down? Raise your hand if you think that's true for first order. First order, does the rate of reaction slow down when you have less and less reactant present? So because the rate is proportional to concentration, as the concentration goes down, the rate also slows down. You have less of it, your rate is slower. Okay? So that means that if you're looking at concentration versus time as a graph, as the concentration goes down, you're going to have this kind of like sweeping arc. So first order, concentration versus time. You're going to have something that as the rate goes down, so does the slope of the graph. Change in concentration over change in time is the rate. What about zero order?
Do the same thing, but it's a straight line.
Does the rate change as the concentration changes? Does the slope of that graph change as you have less and less and less of your reactant present for zero order? Nope, it is a straight line that is the same rate the entire time. What about second order, concentration versus time? What does that graph look like?
Is it just steeper?
It's like first order, except it's much steeper because there's an exponential, a squared relationship between the change in concentration and the change in the slope of that graph. So what I want us to do is I want us to look at a series of graphs, and I want you to determine whether this is zero, first, or second order. So let's do numeric. What is the rate order for this reaction? So look at the concentration, look how it changes with time, see if you can come to a conclusion of whether this is zero, first, or second order. And we're going to do a 10-second on this one, and then I'll give you some more information that might help. Five seconds. Select an answer. Send in first, zero, first, or second. 0, 1, or 2. Hit send. Okay, it looks like we're split between first and second order. What else would you like to see in order to decide whether this is zero, first, or second order? A graph of what?
Of the concentration.
Of the concentration versus time. And if it's a straight line, we know it's zero order. And then first or second, it's a bit hard to tell. What other graphs would be really useful?
Log
The natural log of concentration. So it turns out that if we have a first order reaction and we take the natural log versus time instead, that is a straight line. And off the top of my head, it's a negative slope. We'll go through here. So what I did here is I took every single concentration point and I took the natural log of it. And I took every single concentration and I did 1 over the concentration. So now we have a lot more information that tells us one of these is going to be a straight line. We can actually graph them, and here's what we see. So what your primer was trying to set you up for was to say that we have some concentration versus time, right? That's the middle graph for this reaction. If we take this data, we say, well, it is not linear. Concentration does change the rate of reaction. As we have lower concentration, the slope changes. So this is not 0 order. It's first or second, so you guys are all right there. Then I can't really tell very well if it's first or second order. But we find that if it's first order, the concentration and rate change proportional to each other, then taking the natural log of the concentration and plotting that versus time would give us a linear function. It doesn't. So we know that this reaction, that didn't help us get a straight relationship, but taking 1 over the concentration did. So this is a second order reaction. Is that what you got out of your primer as well? So we hold on to that. So how would you describe where we find the rate of reaction? And which of those 3 graphs would we find it on? The slope of which of the 3 graphs that I just showed? Which of these 3 graphs would you find the slope? Is it this one here you find the rate by finding the slope? 1 over concentration? Nope. The rate of reaction is change in concentration over change in time. Which only one of these graphs can we use to find the change in concentration over change in time? Stacy? The middle one. This middle graph, concentration versus time, if we find the slope at any point in this graph, we can find the instantaneous rate of change of concentration. So then what's the slope of the graph on the right going to give us? K. It'll give us the rate constant K, if it is second order. And the rate constant is always a positive number, so this happens to be a positive slope, so that's our rate constant is that positive number. For the other 2, the slope of the linear graph is also the rate constant, but sometimes it's negative slope. We just know that K is always positive, so we just invert that sign. So let's take a look at this one. See what you think. I think this is multiple choice now. 0 first or second order. I'm going to give you 15 seconds to decide whether this is 0 first or second order. Five more seconds. And closing out. All right, who knew that immediately without looking at the numbers, what order this is? Anybody? You don't even need the numbers. Why? What kind of reaction is this? Radioactive decay. All radioactive decay is always first order. Okay? And then first order means that as you change, I think I have all the data here, so I have 1 over and I have natural log of those values. You can look and you can say, okay, well the time change of 5 seconds, 5 seconds, 5 seconds. If we want to find the slope, right, we pick change in concentration over change in time. So first order means that the change between 0 to 5 seconds should be the same in natural log as from 5 to 10 as from 10 to 15. So if you look, it's about a 0.25, 0.25, 0.25 in change in natural log of radioactivity. You kind of see where I'm doing that? So you could just say, well, this changes the same steps as this, if this is a constant change in steps. I prefer a graph, personally. All right, this is way easier for me. I can see the natural log of concentration versus time is linear. So if I want to say, I want to find the rate of reaction at 20 seconds, how do I find that? How would I find the rate of reaction in 20 seconds? Would I go up here and find the slope of natural log of radioactivity over time at 20 seconds? Or 20 minutes, sorry? No, that's going to be my rate constant. It's going to be the negative rate constant, right, because it's a negative slope. So I would have to go over here to my left graph at 20 minutes and find the instantaneous slope. That's one way I could do it. What's another way? We know that the rate law says that we can find the rate is equal to the rate constant. Do we know the rate constant for this reaction? Could we find the rate constant for this reaction? What is it? The rate constant is the slope of this graph that's linear. Right, the positive of that. Times the concentration. So we say, okay, at a time of 20 minutes, we could find concentration, and then we could potentially find the rate. Okay, so that's one way. Not very easy. If you flip to the very last page on your packet today, you'll see some of the equations that might have been mentioned to you in the primer. So if you have a first order reaction, then all of those equations are going to allow you to find out more information. We already talked about the differentiated rate law. Those are the ones we did up until now. The rate equals this thing I just wrote up here. This is called a differentiated rate law. The integrated rate law says that the slope of this line is our rate constant, and then we can tell how concentration changes over time from all the information in that. So for a first order reaction, we know that the straight line formula of that line, our y equals mx plus b line. Everything we're going to try to do, as chemistry, we love to simplify things. So for first order, we said that the slope of the line is our m, right, negative k. Our x value, right, the x-axis was time. The y-intercept was the natural log of our initial A naught. That's our initial concentration at time 0. And then our y value at any particular time is the natural log of the concentration at that time. So this allows us to make predictions much better than what I just talked about with that other equation. So would you be able to answer a question like this? How long until only 3.7% remains? Try to write it out, and I know we probably need to wrap up in the next 30 seconds. Think about how we use that equation that we just talked about to answer this question. And this is kind of on your homework, so I kind of want to set you up for it. So is anyone willing to kind of start us off? So I'll put our equation up here, natural log of the concentration at time t equals negative rate constant times time plus natural log of the initial. So for this particular question, what is our concentration at time t? If our initial is 100% radioactivity, so natural log of 3.7 equals negative k times time plus natural log of what's our initial concentration? 100. We have two unknowns though. Can we figure out one of those two unknowns? Do we know one of those two unknowns? What is our k? How do we find that?
The slope of the straight line graph.
So we can pick two data points as far apart from each other as we can. We can find the slope of those that we know is linear. So can anyone do that real quick? change in concentration over change in the natural log of concentration over change in time. So that's negative 2.9. What is it? 0.6. Over 60. Does that sound right? Is my math right? 2.906? Or am I wrong? No, it's 2.996, right? Are you seeing where I'm getting these numbers? So the change here is a decrease in natural log of 2.996. I don't know why I said 3. 2.996. The change in time during that same interval is 60. So what does that come out to mathematically?
Negative 0.0499.
Everyone seeing how I got that K value? That rate constant? What's that?
But aren't we going to make it positive?
Yep. So our K is a positive value of the slope. So this is really a slope. So then we can put that value in for the K at the top. 0.0499. How much time do we think it's going to be? What do we know it's going to be more time than? More time than 60 minutes. So can someone solve for the time there and see what we find? Natural log of 3.7. Someone raise their hand when they get it. Bertha? I don't know. We didn't put units here. Oh, it's minutes. Right, it's on the x-axis. Does that number make sense? Yeah, it seems like it. If we kept going past the end of the graph here, it wouldn't be too much longer before we actually get down to 3.7. So what we have now is two very powerful things. We say, if we change the initial concentration, how does the rate of the reaction change? But that doesn't really help us with how long until we have something left, and that's what the integrated rate laws do. So that last page summarizes a whole bunch of ways to do this. We can only use that equation for first order. If we have second order or zero order, we have to use another equation in order to get that. So this next week will be practice, and then Monday we'll get to do this a bit more. I don't think your homework is going to push you too far this week. It's a lot shorter than the ones you've had in the past. But if it does, feel free to post on Blackboard. I had a couple people post on Blackboard. It was really useful to reply for POGO 36. If you have not completed POGO 57, that is all about this. It's all practice for this. So I'd highly recommend, there's some more at the front there. Try to work through POGO activity 57. That's the one that was yesterday or today. And that should help you move forward. All right, thanks for your patience. I apologize for going long today.